Yeah. And don't worry, I'll change my hats between being an organizer and a speaker. So no problems. Okay, so let's get started. So one thing I should say, like every speaker in every school says, okay, please ask questions. And I know from my own experience that it takes a certain amount of growing up before you end up asking questions that sound kind of, maybe it's silly, okay? So there are various, that always keeps on happening to me, okay? There are all kinds of sneaky ways around it, okay? Ask me here, that's the best, okay? Because then we can discuss something. If it is something we should postpone, I'll tell you, okay? If we catch me outside, etc. There are some people who are brave enough to give me some feedback, and I can sometimes see that certain very basic things were not clear. So I'm not going to go over the whole talk again, but at least remind you the salient points, okay, before we get started. Okay, so what were some of the key issues? Well, you don't need a reminder of the broad motivations that in biology there are many different potential causes, many of which are most probably zero or not much of an effect, and and we are kind of, if we take a very complex biological system, we are always kind of data poor. We have really very little data, and we have to make some assumption about the nature of the influences, right? And then try that out, right? So that bit is clear to you. So then what I said is that, yeah, this is the part that may not always have been very clear to you, is that, so these are all examples. I'm trying to solve some kind of underdetermined problem. Maybe better to show it this way. It's a rectangular matrix. I have a lot of x's, and many of them are zero. And we are in the region where the number of non-zero things is less than the number of measurements, okay? So there is some hope we can reconstruct it. Trouble is that we don't know which ones are non-zero, and there is a very large combinatorial set of possibilities. And I argued that, okay, you could go that way. You can look at all the combinatorial possibilities, and you will, in principle, then find the answer for the typical case of a random matrix here and some random sparse vector here, okay? But the point is that that's not always very efficient. And then I tried to explain that I can replace this problem by a different problem, okay? And this is where apparently some of the notational trouble began, okay? I have this vector y. I have minus h times x for any trial x, let's say. Okay, these two should be as close to each other as a vector. When I square this vector and I try to minimize it, it will love to be 0. Okay, and if it becomes 0, then y is exactly equal to hx. The trouble is that if I have too many x's and too few y's, there are many x's. There is a whole continuous space of x's, right? That on which y is going to be equal to hx. And I gave you some kind of trivial example like this: one variable, one y, two x's. I have a linear combination. And then there will be a line, for example, in x1, x2, where things would be 0. And I want to lift that degeneracy, okay? And the way you lift that degeneracy is by using some kind of regularizing term. And we had some discussion about regularization that are like x squared. But if you do the L1 norm, which is just add up the absolute values, this has the habit of producing sparse solutions. So for example, I have a degenerate space like this in the 2 variable and 1 measurement case. And if I minimize the L1 norm is constant on these diamonds. The minimal one would pick actually a sparse solution in the sense that it will pick one component to be 0, right? Now, the part that may not have been clear is that here is a well-defined optimization problem, a convex optimization problem, for which we have good algorithms, right? I definitely get an answer. Question is that, is this my original answer? Is that the x0 I started with to produce y? I can produce y as hx0, and I do this optimization problem. I am not guaranteed that I'll be getting the same x0 back, right? And what I said then is that it turns out that if I look at the parameter space in terms of these two scale parameters, one was the number of non-zero components over n, and the number of measurements over number of possible variables. In that space, there is a region where with great deal of, for larger matrices meaning K and M all are pretty large. Now, you will see how large is large, okay? Okay, you won't see, but I'll show you some examples, right? If these things are large, keeping the ratios of M over N fixed and K over N fixed, right? Then there is a sliver of this phase space where actually you reconstruct the solutions pretty well, okay? And there is this part of the phase space where you should, in theory, if you do that horribly combinatorially expensive way of doing things, you should be able to reconstruct the answer. But we need some method for it. There are other algorithms which might have boundaries a little bit further out, right? And then there is this region where you cannot quite do it because really you have to determine more than m variables with m pieces of data, okay? So, and I showed you this picture where I said that this is practically those two axes except x and y has to be interchanged and this guy has to be flipped over, okay? But you kind of see the shape is roughly the same, okay? These are the regions where this is the famous work by Donoho and Tanner where they show that this whole region, you almost with probability 1 reconstruct the right answer, whereas, and then it very sharply falls off past a certain point. And I showed you some error profiles, and I kind of want you to be reminded that I'm sending these things to large numbers, keeping these ratios fixed, okay? Right? Now, what I thought actually is to see a little bit, okay, get out, yeah, how large is large, okay? Right? And that we do as experimental mathematics. Now, there is this famous stories about the Pauli effect where all demonstration experiments would go wrong whenever he's around, right? And even with computers, things go wrong with me. So we have the computational Pauli effect, but I'll try, okay, to show you, okay, you know, how big those things are. I say they go to infinity, but sometimes infinity is not that far away, okay? So, for example, let me try this one. So I have a bunch of things I have. So for example, here is some matrix that I'm going to generate. Okay, what is it? I'm going to generate a random sensing matrix, which is 50 this way, 200 that way, okay? So kind of rectangular, and one side is 50, okay? So here, okay? So if you want to look at H, it's a very, very full matrix, okay? Sort of it's going on and on and on and on and on, okay? So now I try generating, okay, so this is 200 possible variables, 50 measurements, okay? What do you want to put the degree of sparsity as, okay? So let's go very sparse. Let's make a vector that is like maybe 5. I'm hoping 5 is good, right? Okay, so let's say, so I make a sparse vector. So here is what x naught now looks like. Lots of zeros and few little teeny guys hiding among them, okay? So there's sort of a needle in a haystack to be found out of 50 measurements, okay? Okay, so here is y. I'm going to make it up if I can remember my NumPy things well. Okay, so I've made up y, right? So you see y. Y has at least 50 measurements, lots of numbers, no signs of anything being particularly big or small, right? Now, I'm going to try to run an algorithm that I sort of tried to modify for this purpose. And unfortunately, I decided to run 5,000 iterations, which takes some time, so I have to try to crack some jokes. But basically, so here is a lasso solver, okay? This is what I'm doing. I'm putting y to be this, h I already gave, sigma square is 1, and this is the coefficient lambda, right? This guy, 0.001. It should be small. It actually had to be played around with to see how small is good, okay? So now I have this embarrassing thing that if I press it, it will keep on going for some time, okay? Well, not too much, hopefully. Tell me when it comes out. So what are we trying to do here? I have to find 5 things, right, which are non-zero, okay, among really 200 things, okay? And yeah, it's going to embarrass me most probably. And in this particular, okay, it didn't. So in principle, 5 you could have done somewhat combinatorially, although it is getting kind of borderline difficult, right? But okay, let's see what happened here. So I have x. Okay, if I plot x, because this algorithm needs to be optimized, you will see a lot of numbers, and you see, oh, where is sparsity? Well, that's because I have only run a certain number of things. You can kind of see there in the C of 10 to the minus 5s and 10 to the 6s, right? Can I find anybody? Ah, here is one, 0.19, right? But you now don't know what's happening, right? So let's try to do something. Let's try to plot it, okay, against each other to see what it is, okay? So let me try plt dot scatter x naught x, okay? Okay, now the moment of truth. Okay, so it hasn't done such a perfect job, but actually first look at this black dot there. The black dot is actually all the zeros. So this is, I should have been more fancy and I should have drawn the x-axis and the y-axis. Okay, these are places where x naughts are 0 and x's are 0 as well. So this is the huge pile of zeros and zeros. Of course, zeros came out as 10 to the minus 6 or 7 in that iteration. You see 5 guys standing out. In the ideal world, with lambda going to 0, n going to infinity, it should lie on x equal to y straight line. Okay, it's kind of done that. I'm a little bit disappointed with this fellow, but I know why this is happening. Okay, close to the threshold, there you see the effect of what's called soft thresholding, which you will discuss with finite lambda, right? This is a fairly good reconstruction, okay? And it has done a pretty much a perfect job of separating out what is not important from what is important. If he has not quite estimated this one right, we'll live with it, okay? So let's now try something else, okay? Now I want to make an x naught that's a little bit bigger, okay? So we have 50 measurement, okay? Why not try 35? It's still, oh, no, not 55. 35, right? So now it is still sparse, still less than 50 observations. And how does life go? So I compute my y, and then let me try to lasso this. Okay, yeah. Oh, I didn't compute y. Stupid me. Okay, sorry. You know what? Okay. I might actually have to. Okay, here is the computational Pauli effect. Okay, restart the kernel. Okay, no. It may actually be. Okay. Okay, so when it comes to the real thing, I think we mess up. Okay, maybe we say yes. Yes. One should never try such things. Yes, quit. Very good. Sorry. Where are we? Happening is that my window is in terrible shape. So, and I can barely see where I am. So, okay, I'll give up, okay? Because, oh, no, I can, I'm not going to give up so easily. Okay. Okay. While things wake up, we can, yeah. So okay. So in that case, it did something. Let me see whether I still have this in the, yes. I'm hoping. So somehow percent pace doesn't work here. Okay, so I'll try again. If it remembers well, yes. Okay, this is my H. This is my, no. Sorry. Maybe it's better for me not to do, okay. This, and we are, so let's do y. Y equal to h dot x naught, okay. So that's it. And if I can get to lassoing things, okay, hopefully everything has been calculated or I'll be really embarrassed after all that. But, okay, so tell me what, if I get to the answer and nothing, another set of things don't go wrong, okay, what kind of graph do you expect to see in here? What are you expecting? What if it works and what if it doesn't work? What would it look like? Okay. Okay, let's find out. Okay. There is this dreaded cross that has appeared there. It's kind of like, in the old Dracula movies, right? Something bad is going on. Okay? What's happening there? What is this cross? What has happened is that it has misidentified lots of zero things. It has made very sparse solution, right? Okay, sparse. There are lots of components that are set to 0. So this direction is x, my reconstructed solution. This is my x naught. Okay, so a lot of guys have x equal to 0. Okay, they were not guys where the x naught, the original vector, was 0. Right? And it has actually estimated some non-zero number, okay, for things that are originally 0. Okay? So it turns out that the number of things it's estimating to be non-zero, well, I don't know. Okay? Case looks a little bit smaller. Okay. Right? So and you can actually if you have some code like that, you can play with it to see how different it is from identity. And you will end up seeing that just close to a certain threshold, you will make little crosses and some deformations there. And then at some point, this cross would grow in size, and there will be lots and lots and lots of misplaced things. Okay, so hopefully, okay, this doesn't add anything to what I said. You could have all imagined this. But the point I want to make is that just because I have an algorithm which produces an answer efficiently doesn't mean it's the right answer, okay? And this is one of these cases where the answer is horribly wrong. It's one sparse solution of y equal to hx. It has very little to do with what the original sparse vector was, okay? Right? Okay, so hopefully, let me go back to tamer things like PowerPoint. Sorry. Okay. So the other point I wanted to make, which I forgot to make, is that I did it with 50 and 200. And a problem of 50 by 200 you will see many times. I could have tried something that is even sometimes 20 by 100 and a sparseness of 2 or 3. And you will kind of see that crossover between a good reconstruction and bad reconstruction. So what I'm trying to say is that m and n's are sometimes in tens and hundreds, and you start seeing this effect. You don't have to wait for very large matrices. Okay? So it is very relevant to even small size data analysis. Okay, fine. So now what? Right. So I think I'm going to try the driest of things today. okay? And hopefully I'll end up doing something silly and you will be laughing at me. But other than that, there is nothing much to be gotten. I will try to explain to you, okay, how people think about why it works in some cases and why not. And I believe even if it is sort of very technical, right, there is something to be learned because there is a tendency, actually often helped by people like statisticians, right, where in the department has a little master's biostatistics master's program. You come there, they basically tell you, take R, write programs in R, here is package 1, package 2, know how to download this, and you are done, okay? And I feel that that's not what one should be doing because many things in statistics and probability, you should think with an open mind about why things are happening, okay? So I want to give you some sense of why this kind of transition is happening, right? And I will most probably fail, but you will carry something home. And you can actually explore data, see why something is going wrong, why it is not working out, right? Because with a tool like R or Python or in MATLAB, you can really look in the guts of what's happening, okay? Right? So I want you to think actively. Okay. So this is, next few slides are a bit technical sounding. If it is, but I'll go over them rather fast. Okay, so this is the setting of the problem, right? Trying to understand why this bizarre stuff happens. And I have to apologize for my artwork, not very good, okay? In the morning you try to do free draw and it comes out horribly. So make a sparse vector, okay? How do you make a sparse vector? So that on the average there are k things, okay, choose k by n probability, right? Sample from a distribution where k over n times, we call it rho times. I'll choose it from a broad distribution which has typically non-zero values, right? And the other set of times, I'll choose it from a delta function peak around 0. And I have not been able to draw it narrow enough. But this is a delta function peak, that guy, and this is some broader distribution, okay? So x naught would be a mishmash from sometimes things chosen from here, which are 0, and sometimes things chosen from this wider band, okay? Then, okay, so the weight on the delta function peak is 1 minus rho, and the total integrated weight in the flatter part is rho, okay? Fine. And then you pick a random matrix by picking all its entries to be independent, 0 mean, okay? And I choose the variance to be 1 over m so that every column on the average squared as a vector is order 1. Okay, that's just one normalization. Okay, fine. Now you do something. Okay, and again, this is sounding very theoretical, but okay, it would sound very theoretical, but it's not as difficult as it looks. Okay, so let me try to explain what. Okay, so there is this whole fetish about Bayesian data analysis. Okay, you have heard about it. Okay, you say, oh, the data comes from some probability distribution. Okay, maybe I should do it on the blackboard. There is data x being produced by something, and the probability distribution has parameters. So if it was a normal distribution, you have mean and variance, right? And if I give you the mean and variance, I can tell you how to sample x's, right? So there is some likelihood I can write down. Now, in Bayesian methods, you often do the following. You have to maybe determine the parameters. If it's something, you say, I write the posterior distribution of the parameters given data, right? And then you feel very good because it sounds so deep and principled or something, right? The trouble in life is that most of the time, for anything beyond some rather simple examples, you really don't know that probability distribution. You are hoping that's the probability distribution. So all that function is doing is somehow, it's a way of restricting your parameters in some reasonable way, right? Now, remember what we did for this problem? I was supposed to optimize for something else. I replaced it by the convex problem. The reason I call it kind of quasi-Bayesian estimation is that I am, in fact, using a posterior probability distribution here, but that posterior probability distribution really has nothing to do with the probability distribution that really generated y. The way I generated y is that I sampled x naught from some distribution. I sampled an H from some distribution, multiplied them together, and gave you a vector, right? This is not the posterior of the same distribution. It is something else. And miraculously, for some range of some part of the parameter space, it would still reconstruct the right vector. Okay? So that's the fun part. So sometimes Bayesians have hope. Much as they're feeling very principled, they're just lucky. Okay? The probability distribution more or less ends up doing a good job, even if this is not the probability distribution by which you have generated things. Okay? So what does that probability distribution look like? Well, it's the same function I wanted to optimize. So what is that function? Let's look at it once more. This is h times the difference between x, what is the variable you want to figure out, and the original x naught. And h times x minus x naught square would be happy if they produce the same y. Okay? But then there is still a degeneracy. And then there is this regularization term. It could be any other potential, but there is something. So this guy, this probability distribution will be high when this guy is low, so near the minimum, right? And it will spread out a little bit. And if this parameter beta, this is very physics-like, it's like an inverse temperature. If beta gets very large, right, then the probability would be very concentrated around what the optimization, where the optimization is supposed to happen. Okay? So I set it up as a physics-friendly probability distribution. But actually, these days, you will find many people in computer science, machine learning, work on problems. So they call them Boltzmann machines. They call them energy-based models. They call it Markov random fields to hide the fact that these are physics stuff. So there is no shame in doing a physicsy stuff here. Okay? So if I take this probability distribution, which is really not the probability distribution that generated anything, okay, and I increase beta, it is concentrated around the point where this function is optimized. So it's pretty much an equivalent problem. Now, what normally, so that's the point I was making. This probability concentrates around wherever this was to be optimized. And you can use this probability distribution to try to calculate typically how much error would be there, right, between the real x naught and x. And then what you want to do is that if you tell me how much the typical error would be, you want to average, after you have done this averaging for x minus x naught by dividing by the normalizing factor, okay, you want to average over h and x naught. So I do it for each h, each x naught. I figure out what x's I estimate. We saw one case where x estimated was very close by. I showed you another example where x was very, very different. You compute, okay, what the difference size is, right? But that's very h and x naught specific. But now you sample many, many things and then average the average, okay, over that to find out what you expect typical mistakes to be. Now, this kind of problem where there is somebody downstairs is a problem that appears many times in physics, and there is a whole methodology to deal with it called replica trick. And I will kind of spare you, okay, what that idea is. That idea involves making new copies of things, and with new going to 0, et cetera, et cetera. Turns out that in this problem, if you know how to do this, you write this down, you do the averaging over h, x naught, et cetera, and you just completely forget all about intuition. You just close your eyes and do the right calculation. For the large matrices, you get all the right answers. So it's kind of remarkable. If you try to do it in a more intelligent way, you suffer a lot more. Okay? So there is some value in having a brain-dead method that looks very sophisticated, but actually it's something, a machinery that you crank on. So I would, since I promised that I'll try to give you some insight into it, rather than show you how to do replica calculations, okay, I'll skip this route. But many times when I've tried to do the easy way, I got the wrong answer, and I went back to the replica answer to check which part was wrong and why, okay? So forget replica method, but if you live somewhere near Paris, it's absolutely something you have to know if you want to talk about compressed sensing, at least in physics departments. Okay, so here is the other idea, okay, which I call kind of the poor man's mean field theory, or poor man's approach. So to develop some intuition about how you do this problem, okay, remember I said, okay, if you can't figure anything out, take k equals 1. Take one variable, right, and start thinking from there. Okay, what does this optimization problem look for one variable? So now I have only one x, right? So it picks up one column of that matrix, right? And I call that column like a vector h, right? So I've taken h, x minus x naught square. Remember h, the way I have scaled variances of everything to be 1 over m. I have m components to sum over, right? It's almost a unit vector with very high probability. It's very close to a unit vector, okay? And I just have to optimize this, okay? So this is an optimization problem you should know something about. Okay, so before seeing any more things, tell me what kind of, if I give you an x naught and give you lambda and sigma and all that, what kind of solution are you expecting? Okay, what does this function look like? Try to imagine before you see a picture. Okay, so what does it look like? What are the components like? Well, there is the norm of x, the absolute value of x. That's like a wedge. And then x minus x naught squared is like a parabola, right? So we have given up on the board, but I think I'll create another humorous situation where I'm falling all over. So here is this one function, and here is the other one, okay? Should I try to put it on there? Okay. And does anything erase from there? Okay. It looks very dangerously close to vertical. So, okay. Anyway, where is it minimized? The sum of the two. Okay, what if x naught was right here? Where is it minimized? Then it should be minimized at 0, right? Both functions are right. If I start moving the parabola to the side, what would happen? Would the minimum shift immediately? Sure? Okay. Look, okay, fine. So, okay. Okay, my examples are not that good. Okay, so the point is that, okay, this is the wedge, and I have something whose derivative is 0. I move it a little bit to the side, actually, the wedge would tilt a little, right? The parabola would look a little bit asymmetric and pinched here, right? But really, the minimum would stay at 0, okay? The new, as x naught moves a little bit, it will look like this. It will look like two different parabolas, right, with different slopes, right? As x naught moves more towards the positive side, this angle actually, no, this would be a case when x naught moves to the negative side. This slope is lower than that slope, right? If I go a little bit further, at some point it will tilt downward. And that's where the minimum would move, okay? So for example, if I get a function to be like this, okay, now there's a discontinuity of derivative across that, but the minimum is now at a non-zero value. So you really need to move the minimum some bit, depends on sigma and lambda square, before the answer, the optimum point starts moving, okay? And you can actually explicitly write down the formula, but maybe it's better to remember this picture. This is basically a soft threshold function, okay? What happens is that if you are within the range of something like lambda sigma square over h square, so lambda sigma square is a very key parameter in this whole thing, right? In that region, you just produce 0, okay? And if you're beyond that, then you basically become x naught minus psi, right? So you start at 0 and climb up linearly, okay? So what is this trying to do? Why would I ever do such a thing? Well, imagine there was a variable, right? It is morally 0, but because I have noisy data or something or the other, I have estimated it to be a small, right, number, right? Adding this L1 penalization basically then pushes it to 0. It basically soft thresholds the value, okay? So that's how it sets things to 0. Now, this is what happens if I did one variable, right? And remember, in the final problem that we are trying to work out, we are sending lambda to 0, which means I'm going to shrink this interval, okay? So only for very, very small things would it be set to 0, right? Okay, so this is, one variable is simple, okay? What about many variables? Okay. Right, so many variables get messier, Okay. Okay. So if you look at this, it's most probably not possible to understand anything. Okay. So let me try to see, okay, whether I can do a little bit on the blackboard. Okay, mostly it goes fine. Okay, so what I had done is to do the first problem this way. I had this H vector, right? And I had x minus x naught, okay, which I will call delta x, right? And there was only one component, okay, right? And I squared it. And then there was this norm x, right? Now, for multiple components, let's write it this way. I have many vectors. So these are m-dimensional vectors, and there are n of them. So there are many, 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 many of them, right? There are too many of them. They are all linearly dependent on each other because I have more than, okay, one such thing. And this delta x, now there are many, many variables that for many variables I have departures from the real value, right? Okay? So I do a square of that over 2 sigma square. What do I have? I have, of course, the single variable terms, right? But for each of these variables, say for HA, I have lots of cross terms. Okay, so I'm just paying attention to just one variable, let's say XA, right? So there are all these cross terms, right? If I want to find out what happens when I optimize, let's say I take derivative with respect to XA, okay, I get one term that's like HA square, which is 1 nearly, okay, delta XA. But I get this whole sum of HA dot HB, okay, delta XB, sum over B, okay, plus various things equal to 0, right? Okay, and that's what we are sort of representing here, okay. Now, okay, so before I go there, so what has happened? Okay, I have this as the derivative. I have delta XA plus influences of many of these cross terms, right, which comes as a linear combination there, right? And I have to vary my linear potential, right? So I'm in trouble, of course, if I'm 0, I should rather write some other condition, right? If I'm at some other point, that's good, I can take a derivative, right? But the net result of all of this is that I end up getting the same kind of clipped solution as, okay, where was it? Yeah. Clipped solution as before. What I was doing here is that I took x naught, right? I put it somewhere, and I decided whether it's below the threshold psi or not, okay? And if it's below the threshold, I set it to be 0. Otherwise, I set it to this psi minus, okay, the soft thresholded version, right? What's happening now is that other than x naught, okay, I have this additional perturbation that depends on every other variable being right or wrong, okay? So I again, this is sort of equation heavy, but as you can see, if I held every other variable to be fixed, right? I take some random assignment of every other variable, right? They are usually not what it was originally, the thing I'm trying to reconstruct, right? So there is error everywhere, okay? If I now try to vary a single one variable, right? They see that single variable sees the influence of everybody else, okay? Unless everybody else is absolutely set to its right value, okay? So in this, because I have HA, HB, HC, all of them are overcomplete, I can never avoid overlaps between these vectors. They cannot be all orthogonal. There are too many of them. So there is going to be some influence of other variables, and if any of them are wrong, right, I get shifted. That's the key insight. Okay? X naught appears to be something else. Okay? So the solution now becomes phi of X naught shifted by eta. Okay? Right? Okay. So that's good. Now what are we going to do? So I can begin to see the sources of my error. Okay? I could have, in the previous version, in a single variable, right? If I use this prop thing, right? What's the typical size of my error? I think I have to do my sleepy checks because I have shown some horribly equation-filled thing. Then I've tried to wave my hands and try to write in illegible handwriting some equations there. Okay, so my track record is very bad. Okay, but tell me something is staring at you. Okay, the one variable problem. Okay, what do you think typically the error size is? Yeah. Is it sigma? Remember, this sigma, okay, is really some totally cooked up thing, right? Because it is not really the error in the original probability model. I just created this loss function with 1 over sigma to sigma square, and really what enters into the story is sigma squared lambda. Sigma has no locus standi separately. Okay? So, okay, look at the function. Okay? If you did perfect estimation, what's the biggest size of your mistake? Okay, the best estimation in the world should have been the line passing like this, right? What's the biggest error? Well, if you look carefully in the soft threshold function, the biggest error you make is psi, right? For example, if you are psi, you will be declared to be 0. Here, the shift is by psi. If you are within this region still, the error is always smaller than psi. Okay? So it's a combination of the sigma square, which I can actually scale to 1, right? Okay? And the regularization coefficient, right? They determine how much error you make. Okay? Right? So, right. So you can, in that problem, if I let lambda go to 0 at the end of the day, right, the errors are going to get smaller and smaller and smaller, right? There is no way around it. Okay? So, in fact, the question now, if I now agree that what's happening to me is that I have my x naughts, okay? X naughts get shifted by eta, right? And with x naught getting shifted by eta, I end up having actually a little bit of a mistake, right? And I pass it by soft threshold, right? Then how do you think I can ever get bad answers? Why am I getting wrong answers? Okay? Or I can even state it this way, right? Okay. So what have I gotten here? I have started out with some x naught, right? I have taken that x naught, and then I have gotten it shifted, okay, by this combination of errors from other variables, which I call eta, okay, right? So instead of x naught, I now live on x naught plus eta, okay? Then this x naught plus eta gets soft thresholded by this function, okay? Where can the error come from? Okay, is it still typically of the size of this threshold, psi, which I'll later let go to 0? How can I get a solution that has a lot of error? Remember, we saw that there was this majorly wrong problem where a lot of zeros were misidentified and a lot of things were set to 0 that were not 0. How can that happen? So how can I now begin to understand when and where I can get large error? Well, I have to have some kind of ways of figuring out a self-consistent measure of eta. Okay, so let's actually try to see what that would be. Okay, what is my eta? Eta is really this quantity, okay? Some h dot delta x, et cetera, okay? So if you look at it, you know intuitively it is related to the size of errors in this variable. But then I can actually do something simple. I could go there and say that this is going to get harder to see. Okay. So what's my function here? I have HA, delta XA, sum over A squared, right? Okay? So what do I get? I get a bunch of diagonal terms and a bunch of off-diagonal terms. Right? A not equal to B, or A greater than B. Okay? So when I differentiate this, okay, what are HA square? What's its typical size? Well, HA square is sum of M, okay, square of numbers, each of which whose square is order 1 over M invariance, right? Now, one of the things that enters into this discussion again and again, and maybe I should have had a slide for it, is that when you sum over many, many, many variables, right, this thing almost becomes the number times its average, right? You know of central limit theorem, right? And law of large numbers. So there is a little fluctuation around it. It's order square root n, okay? But the sum would be order n and the mean, right? So if I have each of these HA square, each of HIA square to be order 1 over m, because I'm summing this over every I, and I there are 1 to m, this thing on the average is going to be just m times m, so it's 1. Okay? There is a little fluctuation around it, but for most practical purpose, it doesn't matter. Okay? So I take this HA square off. Okay? So life gets easier. Okay, now I differentiate and see how much shift I get. So I get delta XA here, right? And I get sum over B HA dot HB delta XB. Okay? Right? Fine. Now, the big question is that what's the size? So this is practically, with a negative sign, my eta. Okay? Right? So what you want to understand is how big is eta. Okay? So what I have done, I have gotten lots of variables order 1, delta x, many of them. I have multiplied them by a vector, right? I have actually taken another vector, and I have taken a dot product in an m-dimensional space. Okay? What's the size of the overlap between two m-dimensional unit vectors, typically, in an m-dimensional space? I think I have to do my second sleepy check. Okay, if I have 3 dimension, I pick a 3-dimensional vector, okay? And I ask, what's the size of a projection to any particular vector, right? I choose a direction, and I say, what's the projection of a random vector on a particular direction? How big is it typically? What is the square of the projection? Okay, what's the projection on x-axis? Typical size of the square of a unit vector. What's the average projection of a unit vector on one of the axes? Okay, so if I have 3 axes and contributions I add up, what do I get? I get 1, right? So if I have 3 axes, the projections on each of these axes on the averages, in an m-dimensional space it is 1 over m, good, right? Now, if I actually take an arbitrary vector, right, and I look for its projection of this vector on that, how big is it? It has to be the same, right? Because I have an isotropic distribution of unit vectors. No axis is, no direction is particularly special, right? So that means HA dot HB actually going to be of the order of 1 over root m, right? Okay? And each of these vectors are independent. So these dot products are independent, okay? When I square it, it's going to be of what order? It's going to be of the order of 1 over m, right? Times, of course, the typical delta x square. Okay? And how many such contributions do I have? How many b's do I have? B's are number of variables. Number of, remember, potential variables, they are humongous in number. Okay? Okay? Number of b's is order n, right? It's just, I've taken out only 1. So this is actually n. So in some sense, this is part of the key insight. Okay? And I'm sorry I've done it very badly. But the point is that that error that you see, this eta here, has capital N contributions, each from a potentially confusion creating, okay, variable. That's actually the trouble of having a complex model. Remember, again, go back, if you are really confused by all these terrible things I'm doing, okay, think of the problem we started with, 1 gene expression, lot of different SNPs. More SNPs you throw into the game, and so, okay, let's think in concretely in that problem what's happening. I have like 100 strains I'm sequencing, right? Okay, I have millions of SNPs I'm interested in, okay? Well, these millions of SNPs, okay, and only 100 of them, that's maybe 100-dimensional vector, or millions of them, there would be kind of accidental overlaps between them. So, by chance, some SNP, okay, their profile across the strains or individuals in a genetic population genetics experiment is going to look somewhat similar, right? And this overlap is the source of trouble, okay? So if over the data set, the genetic profile, for example, is almost the same, but just by accident, right? Then my method is getting confused, right? It should get confused. And the way it shows up in this whole calculation is that this extra confusion caused by misassignment in other variables, okay, start making this contribution. Note that if these were all orthogonal direction, okay, there would be no problem at all, right? You can make a mistake. My mistake is independent of your mistake, okay? So the key idea, therefore, is that the way I try to solve this problem, right, I have my x naught. There is the confusion caused by every other variable in the world, right? That gives you a shifted guy. And if this shift is big, then I'm in trouble. This would be this is how I will get to a self-consistent equation for error, okay? I will actually try to say, give me the distribution of x naught, decide there is a certain variance to eta. I solve this this soft thresholding problem. I take x plus x naught, run it through the soft thresholding function. I get some x. I calculate the error, right? I square it. I estimate it. And then I hope some relationship is like this is true, okay? And the key thing there is that downstairs there is this parameter alpha, right? So more data poor you are, okay, smaller the alpha, right? So if you have many variables and very few observations, right, then alpha is a very small number. And the size of errors get amplified by a factor of 1 over alpha to make this eta size bigger. And therefore, at some point, at some small enough value of alpha, your errors would start dominating, okay? In other regimes, what would happen is that the errors would be of the same size as the thresholding value psi, and as I let psi go to 0, the typical error would also go to 0, and I'll get a self-consistent zero error solution. Okay? So that's the whole thing. Okay? But so we are done, right? We have set up the problem. We have done everything. We now will get a self-consistent equation for the error, and then I can figure out when error is 0 and when error is non-zero, and I'll get my phases, right? Okay, now turns out, this is why I said that we, unfortunately, okay, the system is much more subtle than that, okay? This would be true provided certain number of things are true, okay? First of all other delta xb's are nearly independent of delta xa. All other delta xb's are nearly independent of each other, okay? The HA.HB's are nearly independent of each other, and actually none of these are true, okay? So, for example, if I had set this delta x to be 0, okay, and I optimized over every other variable, and then I suddenly say, oh, I'm now going to change this, okay, this particular delta x, every other variable I let them relax, actually they change. They change by very small amounts each, but its collective effect back on the original variable is quite big. It's order 1. There are 1/√n effect on each of them, and they hit you back with an effect of 1/√n. So the feedback is order 1/n, but there are n such feedbacks. Okay? So when you add over all those feedbacks, actually delta x, okay, feels the influence of its correlations with everybody else. So that has to be taken care of. Okay? The correlations between delta xb has to be dealt in a certain way so that it doesn't actually end up affecting our calculation. So it turns out that this one actually has to be modified. Okay? And this is the part I said the replica calculation does right. Okay? And the straightforward thought doesn't quite do well, okay? And this is basically the first important modification. The one variable effective optimization problem isn't quite x minus x naught minus eta square over 2 sigma effect sigma square. This sigma has to change, okay? Why? Okay? So it has to, okay, so I'm not giving you a rigorous argument, but if you thought about it this way, I have this one variable effective problem, right? What I'm going to do is I'm going to take out the influence of x changing here, changing everything else, right? I'm going to incorporate that effect into my effective function, right? Then what's going to happen? Originally, this function actually has a certain curvature and a certain dependence, right? Now, suppose I go to another point and I say, relax every other variable. Okay, what's going to happen? So if I keep everyone else fixed, right, this function is like that, right? But if I go from its minimum to some other point and left every other variable relax, right, my sort of every other object relax function is going to be lower, right? Because I have already optimized over everyone else. I didn't hold them fixed, okay? So this function would actually end up having a changed curvature. Its curvature would be, in fact, a little bit lower, smaller than its original thing, and this sigma effective would end up getting bigger than sigma, okay? And so with this problem, we do exactly the same thing. We do the soft thresholding, but the soft thresholding parameter now changes to lambda times sigma effective square. Okay? And then you have a self-consistency equation. This bit, now done right, turns out to be what exactly I expected. Okay? But there is an additional condition, which is sigma effective square is a little bit bigger than sigma, And it depends on alpha and sigma effective itself, but in a rather simple way. In general, things are more complicated, but in this particular problem, it's relatively simpler. And then there is this weird parameter called rho hat appearing there. What is rho hat? Rho hat is the following, okay? I had rho originally. Rho, what was rho? Remember? That's k over n. That is the indication of how sparse your solutions are, okay? And rho hat, on the other hand, is the following thing. I have a stochastic problem set up here. I pick x naught, I pick eta, I do this optimization, and I get an x, okay? Sometimes this x, remember it's soft thresholding, turns out to be 0. And sometimes it turns out to be non-zero. The fraction of time it turns out to be non-zero need not be what originally was the fraction that was non-zero. That depends on whether we are in the good regime or bad regime. So for every setting of x naught distribution and eta distribution, I can figure out a probability of finding x to be non-zero, right? That's sort of my estimated rho, a rho hat, right? So that rho hat appears in this equation, okay? So you can now kind of do this numerically, okay? You can choose a certain variance for eta. Mean is taken to be 0. You take, of course, the x naught probability distribution. You run it forward, you get a different delta x square. You now plug that back, change the variance, and you see what self-consistently comes out, okay? And if you do that right, okay, what you end up getting is some profile. So this graph, unfortunately, okay, is not quite labeled all that great, right? So this is not really alpha. This is really m. So what is going on is that I have 200 variables, and I have 100 observations, but I am actually doing this for 100 observations, 90 observations, 80 observations, 70 observations, et cetera, right? Okay? So when would the error build up? And I keep the same sparsity of x. There are only 10 out of these 200 are non-zero. Okay? Yeah, sorry. Okay. So there would be some level when the number of observation gets to be small enough, okay, that I can no longer do a good job, okay, of reconstructing the variables. So there should be some threshold m, right? And it kind of looks like the threshold m is somewhere close to there. 20 is down there, okay? This is where the error starts building up, okay? And this is my students labeling, and we have to find better ways of doing this. Red is if you do explicitly several cases for random matrices, okay, the error estimate and square and average. And blue is what the self-consistency equations predict, okay? And you see that it does a pretty good job, right, of following what the error is for a rather small size problem, okay? So, what do I want to say out of this? Okay, look, the fact that theoretically, right, you can get somewhere in the very idealized problem of random matrices, okay, and sort of totally uncorrelated entries, x not chosen in some ways, right, that there you can analyze something. It's sort of nice and cool and we love it, right, but it's not actually as important, okay? What is sort of important is what's coming out in the guts of this solution, okay? So there are two crucial things to understand here. One is that because of this m over n effect, right, when I try to optimize one variable, there is sort of misleading, okay, shifts coming from the neighbors. And then there is sort of the effect of rho, right, which I hadn't actually explained very well. But what if I go back here? Okay, so if I had, for example, a very, very, very non-sparse thing. So if I had extremely sparse thing, then most of the time I'm picking things at x naught, okay, in 0, right? And what would happen is that I'll be right most of the time, okay? So let's see, the way to think about it is that do I have a self-consistent small error solution. Okay? If I have errors to be small, then the eta size is typically small. Okay? If most of the things start out at 0, and I corrupt them by eta, and eta is order psi or smaller, right? I will fall inside that little interval. Okay? And I'll get soft thresholded to 0. Okay? And there will be a few cases where I'm way outside, and because the error is small, and because most zeros have been set to 0, your friends don't get you so confused. Okay? So typically they shift a little bit, then they get soft thresholded and then get an order psi error, and you can actually self-consistently get this order psi error problem and then can do that, right? So understanding rho and the effect of H, right, is important. So if you understand where it's coming from, though, the mistakes in the problem, then you can answer questions without having to solve something, right, which are actually away from the ideal situation. So imagine I have a situation where I have some of these things. I have some degree of correlation in the matrix. Okay? Some of the rows, okay, some of the columns look quite correlated. Okay? This would be the case, for example, if you're looking genomically, right? Close by SNPs would be correlated. Okay? Or in some cases where you're trying to solve some kind of Fourier transform problems, right? You have data, you have some kind of time profile, you're trying to do Fourier transform, and you don't know which frequency grades to choose. Close by frequencies produce roughly similar profiles, and therefore, okay, they are somewhat overlapping on a finite train. Okay? So is this going to hurt your case or going to help your case? If some of these columns of the matrix are correlated, how do you think about it? So if you actually remembered where the grief came from, it came from these HA.HB delta XBs. Okay? And even in random matrices, where on the average things are orthogonal, there was a little bit of an overlap, order 1 over root m, and those things squared added over n things piled up to be a huge effect. Okay? If I already have correlated entries, right, then it's even worse, right? This number is going to be even bigger than 1 over root m, right? So in some sense, if I have correlated covariates, this method is going to break down faster. Okay? And this is actually one of the problems with lasso. Okay? If I have things that are very, very uncorrelated, okay, then this minimum random correlation is all we have. Okay? I have, n m-dimensional vectors. Some of them, by chance, would have some degree of large overlap. Okay? But if they're correlated, I'm going to get even bigger effect than that. And therefore, a little bit of error would have a big amplified effect on shifting something. Right? And this is sort of related to something we discussed last time, and I hope to discuss in greater detail later. When we again, maybe I try to use Blackboard. Okay. So if I had two vectors, right, in this space, okay, which are very similar, right? And I have x1 times this vector, h1, and h2 times x2, adding up, right, to produce the answer, right? And I took the ideal case when h1 and h2 are exactly equal, so I have no way of knowing x1 and x2 separately, right? What we saw in that case is that I have some constraint thing like that, right? And I had my diamonds, and you asked the question about the diamonds kind of lining up almost with that, right? So in those cases, quite often, somebody correlated guy through that eta term would produce a big error on me, okay? And I'll often choose completely wrong guy as a result, right? So I could either choose this fellow or this fellow, okay? And if I finally try to see in my plot of x0 against x1, how many things I've misclassified, the number of things would be bigger because there are some zeros I have taken as non-zero, and some of the non-zeros have become zeros, right? So in such cases, maybe, okay, what you want to do, thinking of this as a variable selection, you actually want to say both of these things are possibly involved. I really cannot choose which one should be there, right? So we can adapt lasso to sort of say that in some ways by doing some tests, okay? Or we can try some other regularization that will choose a solution that will keep them to be non-zero, which is what adding a quadratic regularizing term does. Okay, so let me actually try to summarize. I'm a bit short today, but you most probably would appreciate being sort of less of it. So I should have planned it a little bit better. Okay, so these are some of the things I want to say. Okay, somehow it turned out, because of all these ways things get self-averaged when they are sum over lots of things, that actually for large number of variables, the problem is sometimes simpler. We can analyze things much better in that case, okay? There are two routes to understanding how this transition happens, okay? Each is really some way of asking what a single variable doing in the bath of all these other variables, right? There is a very technical way of doing things, which is the replica route, and I decided not to talk about it, although I had a few slides on it, right? That is sort of the surefire way of getting the right answer, okay? And then there is sort of the harder way, which in certain circuits, in spin glass circuits, are called the cavity method, where you say, I take this site, I now remove it, okay? I see what the rest of the problem should be. Now I add the site back, okay? And as I add the site back, rest of the solution change some, they have some influence on it, and I try to construct some kind of self-consistent rule.
The number of non-zero guys comes out of the measurements, out of the data. It's not something that you put in here. So in the regime where it works well, that's fine. You pick out the right number. In the regime where it works wrong, you said that you could actually pick out the incorrect number of non-zero values.
In theory, you can. Now, so I was actually looking at it. Okay, so first of all, this I actually want to look at the self-consistent equation. In fact, tells you what the misestimated number of zero things would be. Okay, but if you play with the examples, you will often see that it's not that it has done the full number, like it's m things. You're actually roughly finding the same number of zeros, but finding wrong entities to be zero. Okay.
Okay, and that's not in the random case. That's in the case where there are correlations, or that's
no. That's in the random case. Okay. What happens with correlation with this whole method actually isn't quite built for very correlated cases. This is what its difficulty is. Okay, and in fact, I guess the point is that if we insist on we could insist on perfect reconstruction. That is one measure to go by. Another is to sort of say what is relevant, okay? So, so I think this method does worse in the second way. If you just say, is it a good regression model, even if you misidentified X, you may actually do a reasonably good job, right? So, yeah.
So, in fact, but adding prior knowledge of the number of non-zero guys doesn't improve the situation much. That's the point.
The way it is set, it doesn't. There's one other thing I wanted to say, because I guess things I touch upon. So next day, it's going to be sort of a miscellany of things, right, that are of I don't want you to go away thinking lasso is the only method, right? Although people who discover it are very happy that they can get something sparse and immediately make a lot of noise about it, right? There are many other ways of getting to a sparse solution, or not even caring about sparseness. Sparseness is by itself not great. You actually might want to know that if your data was slightly different but from the same system, okay, would small things stay small? That's actually much more important than it being absolutely sparse. Okay? And then there are other things like, like maximum entropy method or something that do reconstruct possible interactions, and you want to know whether it's robust, okay, to fluctuations. So that's important. But the thing that I may not talk about is one of these issues, which is that suppose you ran, it's sort of related to your question is that I don't know what the sparsity is. Okay? What if I am given some data, I have constructed the solution, okay, right? I knew what x naught was. So I showed you which was right, which was wrong. Okay? How do you figure out, okay, that you have gotten an answer that's right or wrong? Okay? So any ideas? What would you try to do if you are given data and you have done some little L1 regression, okay? And after that, you found a solution, but you really don't know whether this is the right solution or not. How do you do it in some other classification problems where you have to choose, you don't know whether your classifier is classifying, okay, these people are very likely to get terrible cancer and others are going to dance all over, but you still don't know. Okay. Huh? Okay, so it's kind of in the right direction. Is leave one out good enough is another issue. But broadly, that's sort of the thought. Okay, look, if I am in the good phase, okay, and I'm not exactly sitting in the boundary, okay, somewhere close by, I'm also sitting in the good phase. Okay, you can always dilute out your data. So maybe don't leave one out, leave many out. Okay, so you can actually take your data, take a subsample, take multiple subsamples which are not overlapping to a great extent, and you can do it less and less if you're closer to the threshold, right? And see what you get, okay? If you are in the good regime, just like, okay, so remember, there is a whole region of alpha, okay, which is m over n, where I get to construct the good solution. So if I change m, I should be in the same phase, okay? So now you do that, you reduce m artificially and choose many different m's, okay? And out of that, many different observations, right? So m becomes m prime, and you choose different m prime combination of things, and the x naught you should reconstruct should more or less be robust. Okay? So if that happens, that's a data-driven diagnostics of whether you are in the good phase or not. So in some sense, in the good phase, certain things are not very susceptible to change, right? And it's by that means, okay, you can tell that you are doing well. Okay? But exactly how much you should dilute so that, because if I leave one out, you might say your x, y is still very correlated. That's why you get the same thing, even if you're in the bad phase, right? In the bad, and you can kind of think about it this way. If I just change one constraint, right, is it going to really change my solution? Maybe not, right? So you have to change it quite a bit. But once you can do that and you can test it, you can actually figure out. Okay. Yeah.
So, okay, Bill, let's thank Anirban.